Okay, welcome back to the second lecture on graph pebbling today. So let me recap where we stopped. Our goal, or my goal, was to show you how to construct this data-independent memory hot functions. Remember, script had like this data-dependent thingy, so now we want to construct data-independent ones. And we had like this three-point plan, which, you know, point A, B, C. And I will first show you the bullet point C, which basically says if you want to have data-independent memory hot functions with some high complexity, what you need to do is you have to find some graphs with some high pebbling complexity. And then this ex post facto pebbling proof that I will show you now will show that, you know, this high pebbling complexity implies high computational complexity for the notion at hand, like CC, space-time, and so on. Okay, so that's the assumption we will start from. So, you know, we will later see how to get there. And this assumption was that, yeah, we have some kind of very nice family of graphs on n nodes which have parallel cumulative pebbling complexity n squared over log n. But no, the exact value is not important, but it's high. And at the same time, the space-time complexity is actually not much higher. It's kind of within the constant of the parallel CC. So this was how we constructed how we said we construct the function from the graph. We take the graph, and then we have this labeling function, which simply, you know, there is a correspondence between how to evaluate the function given how a pebbling would look on this graph. We looked at this trivial first direction here, right? We said basically that, look, if the pebbling is easy on that graph, the corresponding function is easy to evaluate because we just emulate the pebbling to compute the function. So this was basically, for example, the space-time complexity for evaluating the function is upper bounded by this pebbling space-time complexity. And now I will show you the other direction, which says that if the pebbling complexity is high, so like a simple combinatorial game, if this is high, then also the complexity in this much more sophisticated computational model where we have like this adversary A who can do arbitrary computation, he has this memory, writes things back and forth and makes this random oracle queries and so on. But yeah, this simple combinatorial game implies complexity in this much more sophisticated random oracle game. And so what we will need is what we will leverage is something that we leverage in countless cryptographic proofs, namely the incompressibility of a random oracle, or of random strings in general, but in this random oracle in particular. And you already said like a first fact that this property gives us, that random oracles are incompressible, is that when we look at the execution of this adversary as he tries to compute this function, we can actually assume that it will never happen that he sees that he uses a label as the input to the random oracle, which he has not explicitly received from the random oracle in the previous round. You know, this is a quantitative statement. There's still an exponentially small, tiny probability that this happens, but for the rest of the proof, we just assume this never ever happens. Okay, and that's where we stopped the previous lecture. So I was just recapping till now for the people who just came in. So let's go to this ex post facto pebbling. So what I want to do is the following. I'm given an adversary who somehow computes the function. You know, this is this adversary A here. He somehow computes the function, making this random oracle queries back and forth. And what I want to do is from this adversary, I want to extract a pebbling strategy, which has the following property. If the computational cost of this adversary was small, then the pebbling cost of the extracted pebbling strategy will be small. And if we know that the pebbling cost for the graph is big, because we proved it, you know, this is a statement that we proved, then we got the contradiction. And the contradiction is this adversary who had the small computational cost to compute the function doesn't exist. That's going to be the proof idea. Okay, so the key idea is to extract a pebbling from an adversary. So how do we do that? Because you see, this adversary is just making queries to the random oracle. I don't know how do I extract the pebbling from that thing. But it's actually going to be very simple. So we look at this adversary. He runs. I look at the transcript, and I look at the query he makes back and forth. And you see, some of those queries will correspond to actually the queries you have to make to compute the labeling of the graph. And actually, I can recognize them, right? I see. At some point, if the adversary wants to compute, say, this function corresponding to this graph here, at some point, if you remember, right, he has to take the input x and compute make this first oracle query to compute the first label. And at some other point, if you look at this adversarial query behavior, at some other point, he has to compute this L2, which means he has to use this input L1 as the input to his Oracle query to get the output label L2, and so on. So I can't see these things. But he could do stupid things. He could make the same query 50 times and so on. But I will extract the following pebbling. I will look at this transcript, and then whenever the adversary makes a query to some, let's say at this point, the adversary received, so what does this mean? These are labels that we see coming from the Oracle, right? And these are basically, this here is going to be the state of the memory that the adversary has. It's not so important what's in there, it's just kind of to keep track of things. What I do is the following. Now, if I see that the adversary receives a label that is actually a label that is used somewhere in that pops up somewhere in this graph, I do the following. I look at this label and I ask, is that label used again in a later time point in this transcript as the input to some other query? And moreover, is that the case, and in between that label, between now that I received the label and the time that this label is actually used for the next time, this label is not recomputed again. If this is the case, it somehow means that this label is interesting and probably should be stored because he computed it now, he uses it later. So what I will do is I will put, here I will actually put I will put the pebble here, this one. Which basically, you have to understand this pebble as follows. This means that in the first step, the pebble was received, and I only keep this pebble, there's no line. I only keep this pebble for one round, which means in the next round, it's used as an input to the Oracle. And actually, after that, the label is not used again as the input to the Oracle before we potentially recompute it again. And then I do the same for this, for this. Oh, and then maybe I see, look, in the second query that the adversary does, he actually receives L2 from the Oracle, right? And if he receives L2, then I look, when is this label used again as the input for the last time? And I see, oh, this is actually going to be in query 4. So I keep it, I put the pebble on 2 and 3, because I don't put it on 4 where it's used for the last time, because in that round it's actually deleted. So I just put it on those two things. And, okay, I could discuss more. But the bottom point being is I'm extracting a pebbling strategy out of these adversarial queries. For this particular, graph that you see up here, the pebbling strategy that I drew down here is basically corresponding to the pebbling strategy above. It means that, okay, at the first step somehow, I put the pebble on, because I received label 1, and that label is going to be used in the future, I put the pebble on 1 and keep it for now, for this round. In the second step, I received label 2, and I'm going to use it in the future, so I keep it for now, here, right? In step 3, maybe, I still keep the label, the pebble L2, but now I also received label L3, and I'm going to use it, so I keep it for now. Oh, and the adversary, so in this transcript, maybe the label L1 popped up again, so the adversary made that query again. Actually, this should be, this is actually corresponding to this here, right? 3 steps later, suddenly there is another query where, label 1 was received. It was used as input, actually, to compute this one. Then it was deleted, but here it was received again. So I have to I put it back again. So this was this thing here. Oh, and then in the next step, label 4 is received. And at this point, actually, I don't keep label N1 and L2 because they are not used for, they weren't used for any future queries. So I didn't keep them around here anyway, right? And so on. Okay, this was maybe a bit fast, but I hope the intuition is clear. Simply look at the transcript, even though, and I know that there are these special queries, these labels that correspond to this function evaluations of these labels in this particular graph, and somehow I map these labels to these pebbles in this way. So whenever I see there is a label coming, that label is used in the future, I just kind of keep it around. I think of this label as a pebble. I keep it simply around till the next time that it's used. So this is kind of ex post. This is called the ex post facto pebbling strategy because it says you have an adversary, he computes something, and after he computed something, I look at the transcript, and then I kind of map it to a particular pebbling. And in fact, because we made this assumption up here that it never happens that the label pops up before being explicitly received from the random oracle before, you can check, convince yourself that mapping a computational transcript where this is the case, where it never happens that the label pops up out of thin air, mapping a computational transcript to such a pebbling strategy will always result in a legal pebbling strategy. Okay. So, if this was too fast, just, you can maybe go through it for yourself later. But at this point, I told you, I have this adversary. He makes queries. I look at these queries that he does. He just has kind of these states, the sigma 1, sigma 2 in his memory and so on. But, from the transcript, I extract this particular pebbling. And that's my first step in the proof. So I have this pebbling. Where do I go from here? Okay, so this is what I said. What I would like to prove is the following. Yes?
The pebbling configuration that you derived, they were dependent on the adversarial randomness, right?
Yeah, absolutely. So the adversary does something, and I take this transcript, and I assume that this transcript somehow computed the label of the sink, and I somehow, whatever this transcript is, this corresponds in that particular execution. Yeah, it can be randomized adversary or not. It's
Okay, so for particular execution, you're not interested in like sort of the distribution over all possible pebbling?
No, in this case, some kind of worst case. You will see why.
Okay.
So, because what do I want to prove? I want to show the following. I would like to say, look, if this adversary somehow managed to compute the label of the sink with small memory complexity. Let me remind you, the memory complexity is this here. It's the sum over sum over each round of the amount of data that he stores in memory. So I want to show that this is large, assuming that the pebbling complexity of the graph that we compute, that underlies the function is high, right? Basically, the complexity is large, at least as big as the pebbling complexity. Always multiplied with the label length because a W-bit label corresponds to basically one pebble. So I make a case analysis. Let's assume in this computation here. So you see, in this computation, I have this state: sigma 1, sigma 2, sigma 3. That's what the adversary stored. Moreover, I kind of each of those states, I somehow, in my mental picture, this corresponds somehow to a pebbling configuration, right? So this state, sigma 3, somehow corresponds to a pebbling configuration with 3 pebbles in my mental state. So let's assume that indeed, when the adversary does this computation, at every time step, for every sigma I, the size of the stuff that he stored is at least as big as the number of pebbles that I extracted, multiplied, with this W thing. So at the adversary does computation, I look at I extracted this pebbling configuration. I look at the state, how much he stored. So the point is, if this is the case for every state, it's not surprising that the adversary did everything correct, because he could just have, I said, oh, there is a label, he computes it, he needs it later, but he basically stores it. So if he stores all labels that he will need in the future for computing future values, that's exactly what's going to happen. The state that he stores is going to be exactly, basically, by construction, the size of the pebbling configuration I extracted, by construction, right? So if he does that, which is not surprising. We expect that to be possible. It's totally possible. But it's also not a contradiction. In this case, you see, if this is true for every I, in this case, this sum here, the sum of all states, if this is the case, the state is always bigger than the pebbling. The sum of all, of the cumulative pebbling complexity, the sum over all number of pebbles over all steps, multiplied by V, is going to be bigger than all the states that he stores. Yes?
One question, do we really need So going through like how you extracted a pebbling out of the strategy, do we really need a random oracle? That was what I was wondering. Because when we look at the last one, for instance, so simply how we computed the last one is like querying the hash function or like random oracle and like the inputs of that one, right?
Yeah.
And the labels. And then if you have like collision resistance, one can also argue that so the previous one should have also been queried.
For now, I didn't use the random oracle property yet.
Oh, okay.
For the extraction, I didn't use it. This is just an assumption. I will show that if this is not so if this is not the case and we are in the random oracle, then I will derive the contradiction.
Oh, okay, but till here, like
till here, I didn't use the random oracle. I just assume it. So this would be like okay. Yeah. If what I'm saying is, even if it's a random oracle, this is not surprising. If the execution is of the form that the state that is stored at every particular step is roughly the number of pebbles that I extracted in my head for this particular configuration, simply because that's what you expect the adversary to do. He has a label, he needs it in 5 steps, so he better stores it. And if he only stores labels that he needs, you're going to have roughly equivalence, right? Sigma I is going to be roughly the number of pebbles times W. That's fine. And if this is the case for every I, we are done, because in this, we don't have a contradiction, because in this case, indeed, the cumulative memory complexity is indeed the pebbling complexity times W. So this is the case 1. So everything, I looked at this transcript, I extracted the pebbling, everything looks fine. Now let's come to the interesting case. Let's assume there actually indeed exists a step, sigma I, where it is the case that this memory that the adversary stores in step I is significantly less than the number of pebbles I extracted, or significantly less than to store one label for each of the pebbles that I extracted. So what does that mean? If you think about it, it means, oh, somehow this adversary has stored much less or significantly less than, let's say, the information needed to encode 10 labels. But somehow, if I run this adversary from the current state to the future, somehow 10 labels will pop up as inputs to the random oracle without having received in the meantime. So what this means is, whenever you give me such a state sigma I can extract roughly, the number of pebbles, pi pebbles, the number of pebbles in the configuration pi, by construction. Whenever you give me that state, I take the adversary, I run the adversary on that state, and I will extract, the number of pebbles in pi by construction. So now assume that sigma I is really much smaller than the number of pebbles times W. But now I can compress the random oracle, and this is a contradiction. How can I compress the random oracle? I basically say, look, I say I'm first going to compress these 10 labels that I'm interested in, and then everything else I just kind of don't compress, but I just learned it clear. How do I do it? Instead of storing these 10 labels that I will extract, I just store this state sigma I, and then the decoding procedure. What it will basically do is I will tell the decoding procedure, look, do the following: take the sigma I, run the adversary, and you will make queries. Answer the queries using your random oracle as you want, like you store all the inputs, most of the input-output you just store, right? Except for a few. And those few, actually, I tell you, those few things, those few that you kind of don't explicitly store are the 10 labels that you will extract from that adversary as he runs. And I will tell you, look, in query 27 from now on, he will make a query where the 7th, whatever in that parallel query, the 7th item is going to be label number 27. So you don't have to store that, you don't have to store that label but you can just extract it from the adversary run on the state sigma I. Right? So again, I'm not going to go through the proof like formally, but the intuition is, if there is a state that is much less than the number of pebbles times W, then from this state, by running the adversary on this state, by construction, I can extract the number of pebbles in that configuration. But now I extracted more information, like I extracted 10 pebbles, each of length W, using something that is significantly shorter, and this is a contradiction. There is some technicalities. You actually have to work out how this decoding and encoding stuff works. This is, there's also this minus small thing here, which is exactly the extra information that I have to tell the decoder where to look for those labels that he extracted and things like that. But if you get the high-level idea, then I think you already you should get the proof gist. Okay, actually, I want to stop here with the part C. I hope you got like an idea how it works, and go to part B. Of let's recap our plan. So what we did now was part C. So I showed you that high pebbling implies high complexity. Now I want to show you that a simple combinatorial property called depth robustness implies high pebbling complexity. And I first have to define this new notion. Okay, what is depth robustness? As I said, depth robustness has been defined by Erdős, Graham, Shemaredi in a paper in the 70s. And it's a very simple definition. It says that a DAG, here, a DAG G on a set of vertices and set edges is ED depth robust. So E and D are integers between 0 and the number of nodes in G. Is ED depth robust if the following is true. If whenever I remove E nodes from the graph, there still is a long path left, namely a path of length D, right? So in some sense, the depth robust, ED depth robust means that, you have a graph that probably has, that was the question before. Probably there is a path you start with and some extra edges. So this graph probably has depth N, where N is the number of vertices. And it says even if you remove E vertices, you cannot really kind of, if it's depth robust, it means intuitively, even if you remove a lot of edges, vertices, there still is going to be a long path remaining in that graph. Let's make an, like, so for example, this graph here that I showed you, I claim it's 1,3 depth robust, in the sense that whenever you remove one vertex, there remains a path of length 3, right? Let's remove this one, then you still have the path 1, 2, even the path of length 4, and so on. You know, you can check it. No matter which node you remove, there's also a path of length 3. I claim it's not 2 depth robust, and I forgot why. So there must be 2 vertices that if I remove them, let's see, this ones maybe, there is no path of length 2. Yeah, it's true, right? There's no path of length 2 left. So you can start here and go over. No, you can't go anywhere from. So yeah, the longest path is this. This is 1. Or no, wait, this is length 2. This has 2. Wait, so did I remove the wrong nodes? Or maybe this is 2 depth robust actually. Okay, I regret. But you get the idea, right? This is maybe a bad example. But you know, how depth robust are like, let's go back to the complete graph in the path, our toy examples that we always look at. How depth robust is a complete graph? If you have the complete graph on n vertices, if you remove 27 vertices on n vertices, if you remove some vertices, what is the longest path remaining? I mean, it's the freaking complete graph, right? So actually, I can draw here. Maybe you see it better. It's the complete graph, right? So if you have if these are the nodes of this graph, like everything is connected with everything. So you know, if you remove some, let's say you remove this vertex and this vertex, I don't care because I just can still visit every single node because I just start at the first topological first node, and I know that there is an edge going to the next one that is not removed, and so on, right? So in particular, any depth, the complete graph is ED depth robust for any ED where E plus D is n. So if you have a graph on 100 nodes, if you remove 50, there is still a path to the remaining 50 for the complete graph. What about the path, not the complete graph? So the path is very non-depth robust in some sense, extremely non-depth robust, because you see if I have such a path, let's say it's such a path like this, I remove, like say, say I remove E of the, like E equidistant nodes on that thing, then suddenly the longest path is no longer n, like this was n, is no longer n, but the longest path is only something like m divided by E. Because I basically chopped up the path of length n using this removing E vertices into n disjoint paths of length n over E. So basically this kind of means this. So the path is only kind of ED depth robust as long as E times D is, you know, basically n, plus some rounding errors. Okay. So here's the theorem I want to prove. That will constitute our point B. So this theorem, this is from a paper in 2017. I forgot where it appeared. It's called, I think, Crypto. The depth robustness of memory hard graphs, I think was the title. It's it's extremely nice and succinct statement, right? It's actually rare that even in combinatorics that you get such nice and succinct statements, which moreover are basically tight. So this is a tight statement. It says the following: if a graph is ED depth robust, then its parallel Pebbling complexity is, so its parallel cumulative Pebbling complexity is E times D. Why is this interesting? Okay, why is this interesting? Because later we will I will show you how to construct ED depth robust graphs, which where E times D is basically n squared divided by log n, and this will then finish. Yes.
Pebbling complexity. This says that the Pebbling complexity is less than something. Aren't we interested in like the other way around?
Oh yeah. Wait, yeah, it's this direction, right? Sorry, I somehow can't. It doesn't let me write.
Greater equality. Oh, okay.
Yeah.
Thanks.
If it's very depth, yeah. Good catch. Okay. So if the graph is depth robust, it has very high Pebbling complexity. Okay. Let's go to the proof. So let's consider the optimal Pebbling strategy for this graph G. What does it mean optimal? the Pebbling sequence which minimizes which minimizes the parallel cumulative Pebbling complexity. So this is a sequence of Pebblings that minimizes, the sum of the number of pebbles over all steps. I mean, if this term here is the parallel cumulative Pebbling complexity, such a Pebbling complexity, such a Pebbling sequence exists that that actually matches this bound. Okay, so now we have this. Now we do the following. We take those. I don't know if I have a picture. Yeah, let's see. I claim the following. I claim for any d. So d is kind of the depth I'm interested in. So that's, for any d. I claim that there exists a set of nodes, let's call it B, such that the following is true. The size of this set B is basically the complexity here divided by D. That's why I just claimed, right? So there is a set of nodes that has this property. And moreover, if I remove this nodes B from G, the remaining graph is not, complexity divided by D, depth robust. So there is a set of nodes for any d, there is a set of nodes. So if I remove a diffraction basically of the, not a diffraction, that many, right? If I remove complexity divided by d many, there is vertices from the graph, then there is no path left of length d. And I will construct this set B from this Pebbling sequence P1, this presumably optimal Pebbling sequence which achieves equality here. And the construction is very simple. So I look at this optimal Pebbling sequence. So let's assume this is an optimal Pebbling sequence for this particular graph. And then here I look at d equals 2, just for concreteness, like a small example, d equals 2. And then I construct a bunch of sets, namely d0, d1, d2, d3, up to b0, b1, up to bd minus 1. So here it's just b0 and b1. And how do I construct this set? Very simple. For b0, I simply take the pebbles on the configuration p0, and the union of this together with the pebbles on the configuration p2, and the union of this, 0 and 2 is basically d. 0, d, 2d, 3d, 4d, 5d, and so on, right? So I look at these pebblings. I take the first one, and every d pebbling configuration. I take the union of all the pebbles that are on these configurations, and I call this set b0. Yeah? And then similarly for b1, I take this set, union this set. So you see with light gray, so b0 is basically 1, 2, 3, and 4, and b1 is 2, 3, 4. I claim that, so here is the symbol. I claim that on average, the BIs are quite small. Basically it's the Pebbling complexity divided by D. Why is this the case? I mean, obviously, if I sum up the pebbles in each of those configurations, 1 plus 1 plus 3 plus 2 plus 1, this is going to be this complexity here, right? And obviously, the number of pebbles that you see in B0 plus the number of pebbles you see in B1 is less than if you kind of sum each one individually, simply because there could be a pebble in P0 and P2. It's actually, for example, pebble 1 is the case, which here is counted twice and here only counted once. But it's clear that, the average P0, or the sum of the pebbles over the BIs, is less than the sum of the pebbles over the PIs, hopefully. So on average, there exists some BI which has at most this Pebbling configuration divided by D many pebbles, right? Because I have those B0, BI, and so on. On average, they have this size. So pick the smallest one, which will have size at most this. So is it clear how I constructed this set? And I claim that this is exactly the set here. So this set B, has this size, as we just argued, right? It has the size complexity divided by D. So now I have to convince you of the following thing. I have to convince you that if I remove this particular set from the graph, there is not going to be a path of length D left in the graph. And here is the proof. So let's assume not. Let's assume there is actually some path. Let's go from some vertex V1 up to some vertex VD. That is and this path is in G minus B, right? So I removed the set B, and somehow this path kind of remained there. But let's see. Let Pj, so we have these Pebbling configurations here, P1 up to P whatever. Let Pj be the first time where this particular node is pebbled. right? I mean, everything has to be pebbled at some point. Like we have this stack, every vertex has to be pebbled at some point because we have to pebble the sink. So let pj be the first time when this is pebbled. Now, if this is pebbled for the first time in step pj, this here has been pebbled already at time pj minus 1, right? Because we have the black pebbling rule. You can only put something on in step j here if this has been pebbled in step g minus 1. Now, when has this been pebbled here? I mean, if this was pebbled in pj minus 1, maybe it was because this was pebbled at pj minus 2, but maybe not. Maybe it was pg minus 3, minus 4, and so on. But it was pebbled at some point in the past, and so on. But you can make this argument go through. And basically what this argument shows you is that because this path has length d, right, there must have been pebbles somewhere on that path for at least, at pj. Let's see, this is very. There must have been a pebble at pj, because that's by definition the first time there is a pebble on vd. But there must have been a pebble on pj minus 1, because otherwise I could not have put the pebble there. And there must have been a pebble on pj minus 2, because either at j minus 2 there was a pebble here and I pebbled this point here, or this pebble was there, but this was unpebbled, but there's still a pebble somewhere at pj minus 2. And you make the same argument, and you can make this argument up to pj minus d, because the path has d nodes. So what does this argument show you? It shows you that if there is a path in g minus b, whatever that is, that has length d, or if you look at any path of length d in g, let's say, right, it must be the case that this path intersects, that there exists some sequence of, pj minus 1, pj minus 2, pj minus d, consecutive pebbling sequences, where at one node is pebbled in each of those, one node on that path is pebbled in each of those sequences, right? So for example, if the path has length d, there has to be like 3 consecutive nodes, for example, those 3 here, where it's pebbled. But let me remind you, how was B defined? B basically took a pebbling configuration and every dth of them. So if this is of length d, so if there is this sequence of length d, and I know in this sequence of pebbling configuration, the path always has a pebble. Moreover, I know that every bi is kind of each dth pebbling configuration. So this means that every bi must hit one of those d consecutive pebbling configurations. I mean, what does it mean hit? One of those was taken into the union of all the nodes that define this set, b0 and bi and so on. Right? Here we had I equals 2, which basically just means that if you look at any 2 consecutive pebbling configurations, one of those 2 has to be in b0, and and the same one of those 2 has to be in b1 and so on. So summing up, what I just said is I derived a contradiction because I said there is a path of length d in g minus b. But then I said, if this is, but this means that this path, this means that in configurations pj up to pj minus d, this intersected with b is empty because, yeah, obviously because one second, how do I explain this rest? So I have the path, there is this path, this has been one of the, I explained it the wrong way around just a second ago. So let's explain it as follows. There is this path of length d. I showed you that this path of length d hits, there exists some j that from this j on, it hits d consecutive pebbling configurations, which in particular means that this path has, that each of the b0, b1, and so on must have at least one vertex from that particular path. In particular, that path does not exist, right? So there does not exist the path in g minus b of length d. Okay, maybe this was too fast, but it's kind of, I apologize. I thought I can go through it in my head again till Wednesday, but I didn't realize the talk today. But this is kind of the, okay. People more or less follow. It's kind of, You can, okay. The proof is in this paper, right? So if you want to read the proof, it's actually a half-page proof. It's not very long. Okay. So you know what? Let me skip the last part. Actually, I didn't want to make the proof, the part A. Where's part A? Explain to you how to construct depth-robust graphs, right? This was, so this one. Right, so now I kind of sketched you part B, that depth robustness implied high Pebbling complexity. So how do you construct depth robust graphs? Let me just show you the construction and not mention any intuition or anything. And let me show you a modern construction, which means that, you know, the original constructions by Erdős, Graham, Shemaredi is a bit complicated, but the current constructions are very simple. As always, we start with the path. So, you know, you have a path of nodes and so on. And then you have to add some extra edges, right? And you want to add the edges in a way that make this graph super depth robust. So how would you know, basically you need some distribution of edges. What would you do? You can add a lot of short edges. But if you add a lot of short edges, it's not very depth robust because then I can kind of take like some consecutive edges and cut the entire graph in half, and that's bad, right? Because then you know, there will not be kind of very long, long paths. Or I can take very long edges, like everything is very long. But actually, if you think about it, also this is not very good because every time I remove a vertex, you have to jump over it, and you're forced to take a very long path. You lose a lot of other vertices that you could have potentially taken, right? So you need somehow a combination of long and short edges. So the short ones to kind of not jump over too much if you kind of remove the individual vertices, but some longer edges if I kind of remove a strap of vertices that you can without being too bad. So that you should sample those nodes. Sound. Okay, maybe it's turned. Test 1, 2, 3. Or is it okay? 1, 2, 3. Okay. So I just give you the distribution. The way to construct really depth robust graphs is as follows. You remember, we want something with in degree 2, right? For every node, let's say this is node 1, 2, up to n. For every node I can choose one and I give you a probabilistic argument. You do the following. Let's say this is node I. So first, you sample a random number. Let's call it x, random in 1 and let's say 2 to 1 and log I. So this is logarithm to the base 2. So, you know, if the node is whatever 1,000, I sample something number between 1 and 10, basically, because 2 to the 10 is roughly 1,000, right? So I first sample, and then I sample x prime, which is at random between 2 to the x minus 1 and 2 to the x. Let me kind of draw this a bit nicer, right? So first, for the node at position x, I sample a random number between 1 and log x. In some sense, this will kind of define the type of the edge. If I sample a large number around log x, then I will basically add then in the second step, I will basically add an edge which is quite long, which is kind of as long as in the ballpark of I. If I sample in a small x at the beginning, like 1 or 2, I will add a very short edge, right? So for example, maybe x happened to be 3. Then we sample something between length 4 and 8. Let's say we sampled 5. So what we do is we add this edge from I to I minus 5. And this is what you do for every single vertex. And if you do this distribution, you can actually prove that this is a kind of an optimally depth robust graph. Right? And the intuition is, okay, I'm not going to go into the intuition, but somehow this edge distribution makes kind of very good local expanders on every dimension, no matter how large of window sizes you look at, and these things are very well connected. Yes?
It should be log I, not log X, right?
Yes, sorry, this is log I. You sample a number between 1 and log I, and I'm ignoring issues, what if it's kind of a negative number because there's some rounding issues, right? You just don't do it again if it kind of didn't work out or something like that. So this is the graph called DR sample that, you know, is particularly simple. We don't have, so this is a distribution of graphs that is going to be optimal. We don't have anything explicit. So I cannot give you kind of this is often in combinatorics. Like the random construction has some nice properties, but I cannot actually write you down the concrete thing that would achieve this.
So what's the probability that this graph is going to be a depth robust graph?
You know, it's basically 1 minus something exponentially small in n or something. It's basically 1 for any practice, because n is going to be huge, right? These graphs we look at in practice of millions of edges.
Okay.
So even if a few samples are maybe not as optimal, it's going to be very close to 1. I mean, the practical parameters are, this is a paper by Joel Alvin and Jeremiah Blocky. Practical depth robust graph, something like that is the title. I don't know. Yes?
Edges you have in the graph?
I mean, it's optimal in the sense that, first of all, I said I just want in degree 2. So this bounds the number of edges to n, basically, right? And moreover, it's optimal in the sense that, in asymptotic sense, because there is, you know, there are other results which show that the best you can hope. So how depth robust is this graph going to be? Actually, I think it's going to be something like. So this is going to be n. I think it's something like in the ballpark of n log n or theta n. So this is ED depth robust. So you can remove something like a n over log n fraction of the nodes, and there's still going to be path that goes through a constant fraction of the remaining nodes. And this is optimal for graphs, you know, ignoring the constants hidden in the theta notation here. This is optimal for graphs with in degree 2. Yeah. I mean, if you want to exercise and if you want to try to construct your own depth robust graph, there is a web page called pebblingame.at. Let's see, can I? Okay, I don't want to. So there's pebblingame.at where you can kind of construct exactly such a graph, which with in degree 2 by adding nodes. I think you start with the graph of length 16, and the task is to construct a graph which has the maximal space pebbling complexity. So here we talked about you know, cumulative parallel complexity, but in that web page it doesn't matter. It's the space complexity. You want the graph where you need as many pebbles as possible to actually pebble it. And if, you know, and then you get the intuition. You know, basically, this is the right distribution that I just told you to use for that particular game. But if you use this particular distribution, you never get to the optimal, which is 6. So the record is 6. 2 people found the pebbling configuration which needs 6 pebbles. But they kind of went more structured to it. If you just use this sampling, I tried a few times, I always get like 5 or 4.
Hello. Yeah. Maybe this is a stupid question here. Why the optimality here is important? I mean, you showed the complexity. You have a lower bound of the complexity, but also, I mean, is it keep the efficiency of the non-attacker low as well, or?
Well, why do I want an optimally depth robust graph? Because if I have an optimally depth robust graph, the better depth robustness I have, then I get this. You know, there's point B that we showed. This implies that the graph has also very high complexity, memory, so pebbling complexity, which then implies that it has very high memory complexity. It was step C, and that's what we want. We want a function which has very high cumulative parallel memory complexity. And basically, we reduce this task now in 2 steps via pebbling then to depth robustness to construct graphs that are maximally depth robust. But of course, the graphs we construct still have to have in degree 2, because at the end of the day, for the function, we want to use like a you know, fixed input length compression function. That's why you have this constraint with input 2. But you see, this is kind of, I think, a very nice pipeline of problems, each one individually, to kind of hopefully end up at the end with the concrete MHF. And as I said, because we don't have an explicit construction, we also cannot go and come with a new standard. You know, I mean, we could say, you know, pick an IIS key and use the randomness of that IIS thing to sample the edge distribution on that graph. That's going to be good in practice. It would be even nicer if you could have something very concrete, like not pseudo-random or something, but just say, you know, this is the edge distribution. We tried something. We tried using edges of length 2, then 4, 8, 16, and so on, powers of 2, which is not quite there. It's kind of n squared over log squared n instead of n squared over log n, but almost. So this had a little bit too much structure, this particular thing. Okay. And so are there questions on the memory hardness thing? Otherwise, I would use the, you know, the remaining 45 minutes. Yes? Yes, there is. It's not tight. Actually, before we knew that depth robustness implies pebbling, there was a paper by Joel Alven and Srebrenko at ETH, where they actually showed that if a graph is not depth robust, then they had some particular pebbling strategies that kind of, can compute the, that can pebble the graph with complexity less than you would kind of have hoped for. Yeah, it came from the other. The upper bound is much more complicated and much more ugly. You have to optimize over one particular value to get it. It's non-tight, but it's actually very nice. There are also very nice attacks. And in fact, these attacks have been used extensively to attack proposers. So there has been this password hashing competition, Argon 2, 1 at the end, where people proposed, amongst other things, lots of functions which they said are memory hard. And then there was a pipeline of papers by Joel, Jeremiah. We also had like one in my group where we over the summer just broke all those functions. And what does it mean, break all those functions? We took these functions, we kind of extracted the underlying graph, which sometimes was not completely trivial because the functions were not described as graphs and then labeling functions, but somehow directly with pseudocode. So you looked at these graphs, you extracted the underlying graph, you proved that this underlying graph is not depth robust by giving some particular, sets of vertices that kind of kill all long paths. And this, using then, Joel's and Srebrenko's, this then implied that these graphs actually are not very good memory hard functions, at least not asymptotically. So typically, instead of n squared, there are these papers which give you this n to the 1.7, n to the 1.5, and so on. So what happened at the end, the graph that won, Argon 2, Argon 2I, stands for independent, is not optimal in this sense, but almost. They kind of changed the edge distribution a few times, and now it's almost the distribution I showed you here. Not quite. I think this somehow, they didn't want to kind of use exactly that. I don't know why. Maybe kind of, it's not that. But Argon 2I is kind of, I think, n to the 1.8 or something asymptotically now, the latest version. So they came close. Okay, so for the remaining 45 minutes, I want to show you one other application of pebbling in cryptography, which is totally different, namely adaptive security. I will skip proof of space because, it's too many topics. Adaptive security. And actually, I want to start with something very simple, namely with the GGM, Goldwasser-Mikali pseudorandom generator. Who has heard about GGM? Okay, most of you. So let me recap it very shortly. What is a pseudorandom generator, PRG? It's a function which takes a n-bit random string and maps it to a string of. Sorry, it's a function that maps n-bit strings to two n-bit strings. Let me use this notion just for brevity, and it has the following property. If you run the PRG on a uniformly distribution of n-bit strings, this is computationally indistinguishable from the uniform distribution on two n-bit strings, right? Even though it increases the length, so obviously the output of a PRG does not have two n-bits entropy, there's only n-bits entropy at most, but it's computationally indistinguishable. And this is typically captured with every polynomial size distinguisher who gets either this distribution or this distribution will output 1 with the probability that differs by at most some negligible epsilon between the two cases. Now, another important primitive are PRFs, pseudorandom functions. So a PRF is a function, so it takes some key. It takes some key and some input and maps to some output, and it has the following security property that if we have this PRF and we instantiate it with the uniform key, let's say UN, and an adversary can kind of make queries to this, right? Sorry, let me key, and this key is kind of uniformly random. So he gets the outputs, PRF, KX. So the distinguisher is, either he queries this PRF, or he queries like a uniformly random function, He will not be able to distinguish one from the other. Obviously, pseudorandom functions are a more powerful or a broader object than the PRG, which just takes kind of one seed, a double seed, that's it. You get that string, you have to say something. With the PRF, I can kind of make queries and get outputs, and it's kind of, very useful. But GGM, Goldwasser-Mikali, showed a very simple construction of a PRG, of a PRF from a PRG. How was their construction? They said, they said, think of it as a binary tree. Think of the key as being the root of a binary tree. And then, think of applying And I will actually make it green. Green is going to mean a uniformly random value from now on. Everything is green is uniformly random. So you apply the PRG. So you get two strings. The left one, which I call K0, and the right one that I call K1, and so on. So you think of this tree, K00, K01, K10, K11, right? So, and because this figure is so beautiful, I'm gonna keep it because I need a few of them. Okay, so how is the function exactly defined? Actually, no, this I just showed you a tree for now. So they said the following. If you get the input, so this would be, you think of that binary tree, and if you want a PRF with input length, whatever, 100 bits, you think of that binary tree of depth 100. So it's a gigantic exponential sized tree with like 2 to the 100 leaves. And on any particular input, say the input is 0, 0, you compute the output in the following way. You start always at the root. Let's say 0. Let's say the input is 0, 0. You always start at the root, right? And then you compute the PRG to get to the lower level. And depending on the first bit, which here is 0, you keep the left or the right part of the PRG output, right? So the first bit is 0. So then I compute it again. I compute these two values down here, and then I actually output this value here. So this was 0, 0. Or if you want 0, 1, it would be I go here and then I go here. I mean, not color-wise, not very. This would be 0, 1. So construction clear, beautiful PRG, and there is a proof. There is a proof that this is indeed, if the underlying building block is a secure PRG, this construction is indeed a secure PRF. How does the proof go? So this is something called the hybrid, hybrid. I hope you have heard about that, but let me recap it. So we basically have two games. In the one game, let's call this the real game. In the one game, you compute the outputs as I just showed to you, right? I originally pick some key, this green value at the top, and then all the outputs that the adversary gets are the leaves of that tree according to the queries as he makes it. On the other hand, I have the random game. So this is where actually what you're querying is a random function. So, whenever I draw something green, it means think of this as a fresh random value, not being computed by a PRG from the value on top of it. So think of it, actually, only the leaves matter, but let me draw the entire tree in green. So basically what happens, you just get these random leaves in the thing. Now, in a hybrid argument, so now I would like to show that if the PRG is secure, the output of the PRG is indistinguishable from random, the real game is indistinguishable from the random game. How do we prove that? We do hybrids, first of all. So we actually consider a few intermediate games. In the case of, let's say, this GGM PRG, what you would consider is a sequence of n games, where in each consecutive game, you kind of make the layer below, from the previous game random. So what is this game here? Let me call this hybrid 0. Let me call this hybrid 2. And this is hybrid. So what exactly is this game in the hybrid 1? It is the following game. I pick actually two random keys, this one and this one, if you want. And if you ask me about this value, I start at this value, compute the PRG, and give you that. If you ask me about this value, I start here and give you that value, right? Of course, in the actual game, you would not compute the entire tree initially and then give you the values, but you would do kind of lazy sampling. You would only compute, the necessary fresh values as you actually need them, but that's basically the methodology. And now the hybrid argument says, let's say you can distinguish H0 from H1 with some advantage epsilon. What does it mean? It means there exists some adversary who can distinguish the GGM PRF from a uniformly random function with advantage epsilon. But then, of course, so advantage is somehow additive, right? It's kind of, then, I could run this exactly same distinguisher, which has advantage epsilon for H0 and H1, on either H0 and H1, or H1 and H2. And if you look at the advantages, epsilon 1 and epsilon 2, he has in these two experiments, epsilon 1, epsilon 2, we know that epsilon 1 plus epsilon 2 must be at least the advantage epsilon that you had for the entire game. Because advantages are additive, right? If I don't want to go through details again here, but if I can distinguish this game from this game with advantage 0.1, and I have like 10 games in between, so then I just run the adversary, right? He outputs 1 here with probability 0.5. He outputs 1 in this game with probability 0.6. And so he has advantage 0.1. But then I just have these intermediate games, and I just run the adversary on this and this. So he will have some advantage epsilon and some advantage epsilon 2 and epsilon 3 for each 2 consecutive hybrid games. And these differences must add up somehow to the 0.1 I have from this game to this game. Right? So this is standard hybrid arguments. I hope you have seen, because I don't want to spend too much time on this. I hope you've seen this. Okay, so, and once I have defined these hybrids, what I can do is the following. I look at, which of the 2 games can the, adversary distinguish particularly well. Let's say it's these 2 games. He really has kind of this epsilon 1. I'm quite happy with it. It's more than epsilon over 2, or at least epsilon over 2. But if I have those 2 games, what I do is the following. So let me draw it. So now I want to distinguish those 2 games. There's nothing here. And what I would like to do is I have a distinguisher for those 2 games. And what I actually would like to do is I would like to have a distinguisher for, let's see. Yeah, this is very convenient. What I actually would like to have, I would like to have a distinguisher for the PRG, right? So actually what I actually have is these 2 distributions below. So I either have, this output here, which is the PRG output, or I have like a uniformly random output. And I don't know which one of the 2 I have. I have one of those 2, and this distinguisher asks me, make your guess. I say, oh, but look, I don't know which is which. But what I will do is, and let me actually draw them like this, maybe. They could be green. I make them orange. They could be green, or they could be white. They could be, random values, or I don't know which is which. So what I do is, I simply run the adversary for those 2 experiments here on my distribution that I don't know what it is, right? So I simply embed the challenge I got from the PRG distinguisher into these hybrid games of these 2 GGM type PRFs where I simulate something like. So to some level, I always simulate randomly, but on the next level, I embed my challenge that I got from the PRG oracle. And depending on whether I'm in the real or random case, I'm going to be in hybrid HI or HI plus 1 in one of the 2 hybrids by construction, right? So this is I think this was the second hybrid argument ever, the second paper that used the hybrid argument, the GGM paper, and is typically used in, as an example in classrooms for explaining the hybrid technique. But that's not what I want to show you, so that was just a warm-up. Once GGM was defined, so GGM exists for a long time, but people realized that it's actually something much more powerful than just a PR. You can use something much more powerful than just use it as a PRG. Namely, you can use it as something that is called a prefix-constrained PRG, or a key-constrained PRG. So constrained pseudorandom functions are basically pseudorandom functions, but they have like one extra feature. For some kind of predicate, you can not only get outputs, but you can also get like constrained keys. And if you have such a constrained key, it allows you to evaluate the pseudorandom function on a large set of inputs, potentially even exponentially many. And what was, 3 papers observed at the same time, once this notion of constrained PRFs was defined and people realized it's useful, they realized GGM is a beautiful prefix-constrained PRF. I can give you a key for any prefix, let's say prefix 01, or 00, let's say for prefix 00, or let's say for prefix 0, because I have such a tiny examples. So some prefix, let's say for prefix 0, I can give you a key that will allow you to evaluate the PRF on all outputs that have a 0 as a first input. So what would that key be? It would simply be this node here, that value. Because if I give you this value, you can compute the entire tree below, so you can compute all the values of that PRF on that particular thing. So I can delegate keys and give them out. And intuitively, you cannot compute anything else, right? I just give you this node. It was somehow derived from a PRG on top, but this node, you can derive all the keys here, but nothing else. Now, how do you define, what is the security game what is the security game now for a key constraint? This particular example of a prefix constraint PRF. Right? Let me make one more example. For this PRG, so for the GGM PRF, right? I told you, look, you simply kind of emulate those hybrids where whenever you play the game, you have to simulate, up to some layer, you just use freshly random values, and below that you kind of use the PRG, or you embed your PRG challenge, actually, if you want to distinguish it. But the game for key constraint PRFs is a bit more difficult, because here the adversary cannot just ask for output, so you can ask for outputs, right? You can say, look, I make a query, please give me this leaf. And you give it, that's fine. But then you can say, oh, I also would like to see this constraint key here. For example, right? Oh, but then you have to give that value. And maybe later he asks, actually now I want to see this constraint key here in the security game. And now, and at some point he makes all these queries. At some point he can say, now challenge me. And what happens is, at this point, when he says now challenge me, he chooses one particular node that he cannot compute trivially himself. He chooses one node where he has not asked for a constraint key anywhere on the path from the leaf to that node. So for example, he asks, this is my challenge, right? And then he either gets this key k, let's call it, key k, this is 0, 1, 0, 0, 1, 0, or he gets something random, and then the adversary say which is which. The game is similar to the PRF game, except that instead of just leaves, you can also ask for the upper keys. But once you have this prefix constraint PRF, this hybrid argument totally breaks down. You cannot do a, like in the PRF game, you had this real and random game. Either everything was real or everything was random. It doesn't make sense to simulate this everything is random game, because let's say you would try to simulate the constraint PRF in this game here, then the adversary could immediately distinguish that something wouldn't make sense, right? He would ask for a constraint key. He would ask for this leaf. Fine, you give it to him. You give him a random value. But then he asks for this constraint key. He says, now I have to give you, okay, I give you a random value. But then he says, okay, look, this random value, if I evaluate the PRG, I get something different than you told me before. I know what you're doing. This is a random tree. This doesn't make sense. That's simply the wrong experiment for a constraint PRF. In the constraint PRF, instead, the real and random experiment look different. And I can show you how they look like. They look as follows. So this is one experiment. So this is the real and random. And they look like this. That's the real and random. In the real experiment, you just have the GGM PRF. You give the intermediate nodes for constraint keys and the leaves for outputs. That's the normal one. And in the random game, you do exactly the same, except for the very last query where you are challenged. He says, look, give me this node. I say, yeah, everything above is kind of not corrupted. So actually, I give you now this random value or not, which exactly captures this intuition that any key that I cannot trivially compute with the constraint keys I got so far, I could have computed myself. So every key I cannot compute myself, I should not even be able to distinguish that key from a uniform random key. That's kind of a strong security, right? But now you're kind of in trouble. How would you do a hybrid argument for this? You want to prove that this game is secure, assuming the PRG is secure. How would you do it? The point is, you really can't directly. But what you first actually have to selectivize this game. So what you have to say is, I'm not looking at the game I just said. I look at the game where the adversary first announces which node he wants to be challenged at the end, right? A very weak game, yes? And then, once he kind of committed to that, then I can give you a sequence of hybrids where you can embed the challenge in each hybrid, right? For example, for these two things, let me actually make this. I just want to draw it for you. This is nice. So, okay, group, copy, okay, paste. This is hybrid. I just paste them down here, and so on. Okay, so this is the real and random, and now I'm going to give you. So first of all, the adversary told me which node he wants to be challenged on. So he told me the challenge node is going to be, which one should we take? This one. This one is going to be the challenge node. So the type of hybrids that you get are look as follows. This one, this one, this one, this one, one more. Okay. So this is hybrids. This is the hybrid 0, the real one. And let's see. Oh, wait. Oh, and this is the random one. 1, 2, 3, 4, 5. You see the difference. Let me remove this. So this is the challenge. Right. The difference between the real game and the random game is only this one node that is now, right? You see, this is one node that is now random. H1, H2, H3, H4, H5. This is this one node in the leaf on the challenge sheet that is random. Before it was not. So this is the definition of the security of this constraint game. This is the real game. This is the random game. That's the security of the game. And here is the sequence of hybrids that I drew for you. And if you look what I did there is I simply kind of put pebbles till I reached the challenge leaves. Then I left the pebble down there, and I removed pebbles going up. Why did I do this weird pebbling? So it looks like a pebbling strategy, right? In particular, if you recognize it, this is a reversible pebbling that I told about this morning. Because I only remove pebbles if I could have put them, right, in some sense. Right, so if I should draw, if I just draw the pebbling strategy, it looks like this. Somehow like this. That's kind of the pebbling strategy. It's a reversible pebbling. It's a reversible pebbling that, assuming that the graph looks like this. So I just drew the pebbling down. And why did I choose such a hybrids, these hybrids? Because these hybrids have the property that now, if you can distinguish H0 from H5, if you can distinguish those two games, then you can also distinguish two of those hybrids. I don't know which ones. Which ones do you want? H2 and H3? Why not? Let's say you can distinguish those two games. So if you can distinguish H0 from H5 with probability epsilon, there must be two hybrids that you can distinguish with probability epsilon over 5, so good probability. And by doing this reversible pebbling, I exactly ensured that whenever I have two games, like this H2 and H3 game here, I will always be able to embed a PRG challenge so that depending on whether that challenge is random or not, I will be the game HI or HI plus 1, one in two games, right? So here, I would basically, if I have a challenge, I don't know if this is, I have a node, I don't know if it's real or random. I have a node, I don't know if it's real or random. What I can do is I can just embed it at that point, and either it's green or white, and then I get the right thing. And I can only embed the challenge if the node above is random, because I cannot, because if it's a PRG challenge, then you would get the wrong distribution. Okay, this was also quite fast, but basically what I don't even want to go too much into detail here, because I just want to tell you how pebbling plays a role here. Now, this proof, this hybrid proofs, is only for selective adversaries. It only works if the adversary initially, yes? Because you cannot, let's assume it would not be reversible. There was kind of a node that was kind of either random or not. So how would you simulate this, right? How would you embed a challenge? Let's say something like this. Okay, and it's, here there was a pebble in one hybrid, and in the next hybrid I removed it. So what does this pebble mean? So now I give you, you're given somehow, and let me actually draw it like this, because I always cheat a little bit because I kind of pretend this is not the, right? Now you're given a challenge, and this challenge is what? It's either like a random string or a string output from a PRG, right? But that string that is output from a PRG here, okay. that string, let's make it quick. So there was some key, which is a square, shown as square, that from which this thing was derived below, right? Now, if I would, whatever I have here, if I would embed it here, okay, if it's random, then I indeed end up in this case. Fine. But if it's a PRG output, then I do not end up in this case. Because actually, these are my two values, XX, I put them here, but they are not being derived from that, PRG key, because I don't know what this is, right? If they're being derived from something else that I don't have access to, so the simulation would just be wrong. So just if you try to embed your challenges, even if this was a bit fast, but if you try to embed your challenges so that you are in one or the other, depending on whether you have a real or random challenge, you really can only embed something if the stuff above is random. And you can also just remove it if it's random, right? So that's the reason, it's very important. Okay, so this is this, we had this game, H0, then we have this game, H5, and it was like this selective, we have these games in between, 2, 3, 4, 5. But this was only a selective game, right? The adversary has to initially say, guys, I'm going to attack this particular input. Let's play the game. But that's not how adversaries work, right? They kind of do the queries and they say, ooh, I think I have like from what I've seen so far, this particular input seems really weak. Let's attack it. There is a generic way to transform any selective reduction, proof that I showed you, to an adaptive one. And the idea is the following. You just take this distinguisher that you have for the selective case, and initially, you just make a random guess, a uniformly random guess, what the choices of the adversary will be at the end. And then you use that uniformly random guess as your, as if it was the commitment of the adversary. Then you run the experiment. And if it didn't work out because your random guess was not what the adversary actually did, you just give up. You just don't make any guess. The problem with this is, if your original selective advantage was epsilon, and let's say we have an n-bit PRF, then after this, making this reduction adaptive, the advantage drops from epsilon to epsilon divided by 2 to the n. It drops exponentially, which makes most security proof just useless, right? So you can have this selective. So here is maybe an adaptive adversary that can distinguish H0 from H1, H0 from H5. Then you basically go down by guessing. Right, so here you had like this beautiful advantage of epsilon. Now down here you suddenly only get the advantage epsilon divided by size of the guess. And the size of the guess is big, right? If it's a 100-bit string, this is not 100. This is 2 to the 100, because there are 2 to the 100 possible 100-bit strings, like this is exponential. Yeah. So basically you lose like an exponential factor. Now, there has been a paper that is called, Be Adaptive, Avoid Overcommitting, which said you can do a little bit better than that. Maybe you have these hybrids here, right? So you have these hybrids here, these orange hybrids. Okay, you can play this game if you guess this big guess initially. But maybe it's possible, if you actually only wanted to, let's say this is kind of, if you only wanted to maybe distinguish those two hybrids, you didn't need the entire guess. Maybe for those two hybrids, you could kind of guess something much, much shorter, and you still could simulate this game, these hybrids, and embed the challenge at the point where you want. And this will. And then there is a theorem which says the following. If indeed you can do this, right? Instead of, I should kind of draw it like, okay, I don't know how to draw it very well. It basically says the following. If you have this sequence of hybrids, and for every 2 consecutive hybrids, there exists a guess of size, let's say, at most m, where m would be much, much smaller than the guess you have to initially make to simulate all the hybrids. If for each 2 consecutive hybrids, there exists a guess that is much shorter, then the total security loss you get from going from selective security to adaptive security is not 2 to the size of the big guess that you need to simulate all the hybrids, but it's only going to be 2 to the m, where m is the kind of length of the shorter guess. Right? So very fast, it's very high level because I want to go to the punchline in the next few minutes. So if you know this, if you know this result, this is a paper, Crypto 2017. It's called Be Adaptive, Avoid Overcommitting. It's like a framework that basically tells you this. It says, if you have like this sequence of hybrids for a selective adversary, if you manage to make these hybrids in a way that each consecutive hybrids only need a little bit of fairly little information to be simulated compared to what you need to do the entire thing, then you lose much less. Now let's see. If I wanted to simulate these hybrids that I showed you here, how much would I have to guess? It's a lot, actually, right? Because, for example, to go from, let's say, from here to here, let's, even from here to here, actually the ones that we looked at, I actually have to guess the leaf. I actually have to know which, I have to embed random stuff all along the path from the root to the leaf. So I have to basically really guess the entire path. There's nothing I can do. So it doesn't really help in this case, right? For this particular sequence of hybrids, guessing the entire thing or guessing just between those two hybrids, which might be where all the distinguishing advantages, doesn't help. But now assume I had like a pebbling strategy. I have this tree. I had a pebbling strategy to get from hybrid 0 to hybrid 5 with much fewer pebbles than, the depth of the tree. But then, what I could do is I could use this general theorem, and I would only have to, maybe instead of 100 pebbles, I only need 10. I only would have to kind of guess. Okay, let me see this follow. So first of all, I have to show you that there exists a reversible pebbling for this strategy that actually uses much fewer pebbles, right? So I had this pebbling strategy before. That's what I showed you before. That was this. So what would be another strategy that uses much fewer pebbles? So here is one. Wait. Yes. Wait, no. Sorry. Okay. I hope you get, this is a pebbling strategy. You can check. It's a reversible pebbling. It's a bit longer than the first one, but it only needs 3 pebbles. In particular, there exists pebbling strategies, a reversible pebbling strategy, with only, now I have to check, how many pebbles do you need? So this length here is going to be n, which is the depth. This one is going to be n to the log 3. It's longer. And the number of pebbles here is going to be n, and here is going to be the solution to t of n equals t of n over 2. It's log n, 2 log n. Okay, I forgot. Let's see, the second. If for n I need something, and 2 I need. Yeah, it's log n plus 1. Log n plus 1. Because the example here is so small, it's not n, it's log n plus 1. So really from linear to logarithmic. And the pebbling strategy is actually defined as follows. It's recursive, right? I can show you the following. You see, if you can pebble, let's say this is n, is path of length 2n, right? What you do is, you first, let's say you have a good pebbling strategy for a path of length n. You first use that strategy to put a pebble here, whatever main pebble. Once you have a pebble here, you can just pretend use the same strategy to put the pebble there, right? And then you kind of remove that pebble again. And if you can pebble a path of length n with k pebbles, how many pebbles do you need to pebble a path of length 2n? K plus 1. Because you just have this extra pebble, right? You need k pebbles to put it here. You keep that pebble here, and then you have the extra k pebbles to put that pebble. And then you have to remove that thing again. That's again k pebbles. So it's kind of this recursive argument which says that, so if you know this, so you can actually pebble a path of length n with just log n pebbles, or log n plus 1. Okay, now how can we use this to get a better reduction for constrained PRFs? The idea is as follows. So I have this gigantic tree. Yes? No, the adversary commits. to nothing. I mean, in the let's see, by selectivizing this adaptive game, what you call selectivizing, we assume that the adversary commits to the output he wants to be challenged on, right? If you have a tree of length depth n, GGM of depth n, this is n bits that he has to challenge with. What?
Basically.
Commits to a leaf, yeah, exactly, to the leaf, exactly.
Right.
And now we want something much smaller. Now I don't want the leaf. Now I'm just going to ask you for a pebbling configuration. Because if he commits to the leaf, he also commits to all the nodes on the path, right? But now what I showed you, if you go from the real to the random, from real to the random configuration, using not this naive pebbling configuration here, but the clever one that has only log n pebbles, you will have a lot of trees like these trees, and in every two consecutive trees, let me show you, in every two consecutive trees, I don't know, this is like this one tree, it's kind of, maybe this is the path at the end of the experiment, I don't know where it leads to. But in each of those trees, you will only have like a logarithmic number of pebbles on the path. I don't know, something like that, right? Maybe this is one experiment, this is the other one. Instead of linearly many, so you have only logarithmically many. So now if you could guess those logarithmically many pebbles, you could get a better reduction, much smaller loss, using this, this general theorem, which says that if for any two hybrids you can make a compact guess, you can do it much better. Now, actually, we've gained nothing so far, because you see, if you have to guess like a pebble down here somewhere, even if it's just one pebble, it's close to the leaf. So you basically, you have to guess the same thing. But the point is, this is a stupid guess. You're not going to guess, I'm not going to tell you, I know there's just logarithmically many pebbles. I don't know where they are. I don't even know what this value is. But what I want to do is, I would like to simulate this experiment. And, of course, in the reduction, then at this particular point, I would kind of embed my challenge so that I'm in one hybrid or the other. Now, what I want is I want some kind of guess, some short string that will allow me, if I knew that string, that would allow me to actually simulate, exactly this experiment. I cannot give you the position of the pebbles. It's too much information. The pebble at the bottom defines everything. So instead, what I will ask you for is, I know where the pebbles are, like on position, like from, this is level 1, they are at level 3, 5, 6, and 27. That's where the pebbles are, so I have to put them there. So what I will ask, what I want the adversary to commit to is going to be the following. In which query, so in particular something else, in which query, for each of those 4 pebbles here, I want the adversary to commit to the following thing. Let's say for this query here, the adversary makes a total of q queries during the experiment. Let's assume, so q is some polynomial, right? I say, which of those q queries is going to be the first one that hits this particular node? And if there could be none, actually, it could be that it's only during the challenge, but I ask you which of these queries is the first one where I actually have to, where I have a prefix that shares the 3-bit prefix with the challenge. And ask which of the q queries is going to be the first query that shares the 5-bit prefix of the challenge, and so on. How much information is that? If I have log n pebbles on my graph, so I need log n pebbles on my graph, I have to ask this. And for each one, there is, log n pebbles. And for each, there is q, some number between 1 and q, which is the q query, right? So the total number of possible choices is going to be something like q to the log n. There are for log n queries, for each one of them, you have to give me a number between 1 and q, so there is q to the log n. It's slightly less even because I know they're ordered. I know that the 5-bit prefix comes after the 3-bit prefix and so on, but if you want, I know that this is at most this many things. And this will typically be much, much, much less than the 2 to the n that you would have to, 2 to the n was the probability that I correctly guessed the challenge node. There are, these are n-bit strings, so I have to guess 2 to the n. So for example, think of whatever, n being 256 and q being, I don't know, 2 to the 20. So log n is what? This is 8. So you get something like, okay, so this may be not such a great example. Wait, q has to be small. No, n has to be big. So if n is very big, this is kind of, anyway, it's kind of, okay, for concrete numbers, actually not so impressive, but for a theoretician, the left thing is quasi-polynomial, while the right thing is exponential, right? So that's typically how you would state it in the abstract to impress people. And basically now, so using this clever type of hybrids, you have this real random game for these constrained PRFs, right? You use this clever game of hybrids where instead of kind of just pebbling the node and going back, you kind of use this strategy that only uses log n pebbles. And then you use this general theorem, which tells you if you have a sequence of hybrids, and for each 2 consecutive hybrids, if there is a short guess or you can think of the adversary just making a much shorter commitment, what he does, and this allows you to correctly simulate the hybrid and embed your challenge. Then the security loss you get from going from, to selectivize the game, so going from selective to adaptive security, is only going to be exponential in this short guess as opposed to the big guess. For this particular case, so this is, the paper is called Adaptive Security of Constrained PRFs. And the point is, don't read that original paper, because when we wrote that original paper, we didn't have that framework. The proof is a huge mess in that paper. It's kind of, it doesn't use pebbling or anything. It's kind of direct arguments that are very complicated. So in this, if you want to read the paper about this thing, I strongly recommend the Crypto 2017 paper called, Be Adaptive, Avoid Overcommitting, which actually, after we had a few of those results, which somehow all had to do something with graphs, somehow pebbly-ish, but not really. So we had this general result which says that, if you can make the guess short, then you only lose something exponential in that short guess. And almost actually all examples we have where you apply, so a priori this general theorem doesn't tell anything about pebbling. It just says the guess is somehow short. Somehow there is some compact information that allows you to simulate those hybrids. But all examples we have for this particular technique where it applies, and this is, for example, for Yarrow's garbled circuit is one, for proxy re-encryption schemes, where you kind of build a graph where the adversary asks, oh, I want to re-encrypt that key under that thing, and so on. Computational secret sharing is one. Of course, generalized selective decryption, which, for example, underlies many of those tree-chem group messaging schemes, right? You have in group messaging, you have these trees, and then people update, so it's basically a graph, and then you have a key that you want to attack. This is very similar to this case, actually. So all these cases, actually, to get this compact commitment from the adversary, it basically boils down to a pebbling question. And basically, it's a reversible pebbling question. So you basically want a good reduction, give me a good, yeah. And last TCC was at, like, for the first time, kind of lower bound. We showed that actually this is necessary. I mean, the loss with using black box techniques, if you look at the underlying graph defining, in that case, it was for garbled circuits, some properties of the pebbling complexity of the circuit underlying this Yarrow garbled circuit thing, some loss in adaptive security is inherent for black box reductions. Okay, so this was kind of super fast. I think I just want to give you a flavor of a totally different application of graph pebbling than this memory hard functions, where it's maybe less surprising, hard pebbling, lots of pebbles, or computations, lots of space. That's kind of an analogy that people see. But here it's really funny, right? So if the reduction, I can only prove it against selective adversaries. And if you look what people did if they really wanted to have adaptive security, they kind of just constructed super heavy tools, like dual encryption schemes, totally unpractical, but they actually could then pull off a reduction with these super sophisticated things. And what this basically framework allowed us was, we just took the most basic schemes, GGM, Yarrow's garbled circuit, and everything, and we got adaptive security for all those schemes, not polynomial, but quasi-polynomial in all cases at least. And in some cases even polynomial, like for group messaging, for example, it's actually polynomial at the end. Okay, so thanks you for your attention, and I will put up the slides for the MHF part. I will not put, this was really just, I will not put these slides up, they're too ugly. But I will put up the slides for MHF, give you to you, and then we put them up. Okay, any questions in the last minute? Okay.
Thanks for the lecture. So using pebbling to prove the adaptive security of GGM, it somehow seems very specific to GGM. So can it also be used to prove security of arbitrary constrained PRFs?
I mean, it's not particular to GGM. It's kind of, any kind of many experiments, many security games that somehow can be mapped on a graph in some way, this thing applies. Now, what is another popular constraint PRF? So there is this bit fixing ones, which are more powerful, right? You kind of can fix a subset of the bits. Unfortunately, you know, there this technique doesn't apply because somehow the underlying graph is kind of exponential, and that's exponentially many edges. If you think about it in this term, there is nothing Pebbling will kind of give you. But we tried very hard, actually. We tried to find the structure. So sometimes it works, sometimes not. So for the bit fixing PRF, it doesn't work, and I'm not aware of any other than GGM, in fact, for constraint PRF. Yeah.
Yep, thanks.
It's probably just the simplest examples. That's why I chose it, actually, to exemplify things.
Thanks for the presentation. Do you know whether this reduction is the tightest possible, is optimal with Pebbling, or do you think in the case of GGM, or there could be tighter reductions?
I mean, I'm pretty sure it's optimal because this is such a simple, you know, I don't have a formal proof. We have now, I'd say that this TCC, we have kind of first lower bound proofs that actually tell something, but it's really hard to prove that this is really absolutely optimal because, what's the reason? Yeah, because it's kind of, it's hard. So I think yes, because I would be very, let's say it like this, I would be very surprised if there's a fully polynomial reduction. It just, if there was one, we would have found it by now, right? So there's kind of a...
Okay. Thanks.